Hello, today we're going to be talking about volume by rotation about a vertical line. Here we're going to explain what it means to do volume by rotation about a vertical line. Imagine that the distance from the y-axis to this line, y equals x squared, is a radius. The area of a circle is pi r squared, and we're going to take the area of circles from the lowest point of interest to the highest point of interest. Ultimately, all these circular disks are going to form a 3D image that we can visualize here. And the purpose of this is to generate 3D models.
Find the volume of the solid that results when the region bounded by the curves x equals y squared and x equals y cubed from y equals 0 to y equals 1 is revolved around the y-axis. Here we're just going to be drawing the graphs y squared and y cubed, and then we're going to shade in the region bounded by the two curves, which is what you'll be finding the volume of when you rotate it around the y-axis. Next, we're going to be identifying R out, which is the curve furthest from the y-axis, and then R in, which is the one closest to the y-axis. And in this case, as you can see by the picture, R out is y squared and R in is y cubed. The general formula using the disk method is pi times the integral from the lowest y value where the curves intersect to the highest y value where the curves intersect of R out squared minus R in squared dy, because this is in terms of y. Then we substituted our example into this formula, pi times integral from 0 to 1, because these are the lowest and highest y values of intersection of R out squared minus R in squared, which was previously identified dy. Using the rules of integration, the final answer is 2 pi over 35.
Okay, so here the question is, find the volume of the solid that results when the region bounded by the curves y equals x and y equals square root of x are rotated around the line x equals -2. So basically, first you want to draw out both graphs to see what your area is going to look like. And then, so since we're revolving around the line x equals 2, we have to solve for x for both equations and then set them equal to each other to get the limits of integration. So from this we find out that our limits are 0 and 1. So then we want to write our R out, and we do that by doing the line x equals 2, so 2 minus the outer graph, which is 2 minus y squared. And then to write our R in, we do 2 minus the inner graph, which is 2 minus y. And make sure to write it in terms of y when you're writing your R out and R in. So then we plug it into the equation, pi times integral from 0 to 1 of R out squared minus R in squared dy. Doing this, we get 8 pi over 15.
Now we want to find the volume of the solid that results when the region bounded by the curves y equals x squared and y equals 4x are revolved around the line x equals -2. It's important to draw the image so that you can visualize the bounded region and understand the vertical line that will be used as a point for vertical rotation. So here I'm drawing the line for y equals x squared, and also drawing the line for y equals 4x. We shade in the bounded region so that we can see the area that we're going to rotate, and draw that. Now we must convert our equations for the lines, which are y equals x squared and y equals 4x, into terms of y. So we must convert them to x equals the square root of y and x equals y over 4. We then set these two equations equal to each other so we can find the lowest and highest points of intersection, which are at y equals 0 and y equals 16. Using our formula, we are going to have pi times the integral from 0 to 16, r out squared minus r in squared. In this case, r out squared is the square root of y plus 2 to account for the distance between the line x equals -2 to the y-axis, minus y over 4 plus 2 squared dy. Using rules of integration, the final answer is 256 pi over 3.